Our speaker today is Anna Schenfisch, and she will be telling us today about ordering classes of descriptor types by their ability to faithfully represent shapes. Take it away.
Cool. Thanks, Lisa. Thanks so much to the organizers for the invitation to speak. I'm really excited to be here today. So I'll go ahead and start by acknowledging my collaborators. What I'll talk about today is joint work with Brittany Fazy at Montana State University, David Millman, who's in industry now, as well as Samuel Mika, who's at Western State. Here's a grant acknowledgement. All right. So after some background, there are really two main chunks to today's talk. The first is exploring what I'm calling a minimal faithful set. I'm kind of getting our feet wet in the area, and then using that to then begin discussing ordering strength classes of topological descriptors. So let's start with the background. So everything I am going to be discussing today will be with respect to lower star filtrations. So suppose we have some underlying simplicial complex shown here in gray, embedded in Euclidean space, and we've chosen a direction like this up direction. And how we filter through this space is we ask what's the subcomplex at or below every height. So here we see our first connected component, just a single vertex. An edge appears. We see our second connected component born, third. We eventually see our first cycle appear, right? Our first one cycle. And we might see deaths where two previously disconnected components merge at this height. And then past the top height of the simplex or the complex, nothing really interesting happens, and the filtration is essentially over. Okay. So throughout the filtration, we can choose to keep track of some sort of information. So for example, in the first half of the talk, we'll focus on keeping track of homology. We could also keep track of Euler characteristic number or Betty number, or any sort of thing you can imagine. And that gives us some sort of summary of our filtration. Okay, so if I keep track of a different invariant, I'm going to get a different summary. Also notice that if I chose to filter, for instance, in a different direction, instead of up, maybe I come sideways, that's going to also give me a different summary and a different filtration. All right. Okay, so maybe for this crowd, maybe the most familiar type of topological descriptor is called a persistence diagram. I'm calling this a non-augmented persistence diagram for reasons that will hopefully soon become clear. Just to quickly refresh, right, we have the x-axis corresponding to at what height did something first appear. Here we're talking about connected components at each 0. And then the y-axis, we keep track of at what height did a connected component disappear or merge with something that was previously there. Okay. And we also have what I'm going to call an augmented persistence diagram. This sometimes might be called ephemeral by folks at the Ohio State, or I think KTH. Today I'm going to call them augmented persistence diagram. And what's the difference? Well, immediately we have all these on diagonal points, right? That's a clear visual first difference between what was on the previous slide, our non-augmented diagram. So what are they doing there, right? Well, they're actually often computed in standard persistence algorithms, but they're discarded because in most applications, they would correspond to noise. They're just not informative, not interesting. They're kind of an artifact of the algorithm. For us today, they're actually going to be crucial, as we'll see later on. And how can we think about them? Well, they're instantaneous events, right? The birth time equals the death time, so they have kind of a zero or a trivial lifespan. And where are they coming from? It's the events that would have happened if we made our filtration step by step, so simplex by simplex, called an index filtration. So let's look at this bottom on diagonal point here. How can we think of it? Well, at the height of this vertex, what's happening in our index filtration if we were to step it out simplex by simplex? Well, we would first add this vertex here. We have a second connected component that appears. And then as we add the edge, that connected component immediately merges with the component that was previously there. So for an instant, we have another connecting component, but it instantly dies. So that's where this on diagonal point is coming from. Okay. So we've already seen two different types of topological descriptors, right? We have our augmented persistence diagrams, which I'm going to denote row with a little hat. They have on these on diagonal points. And then our non-augmented diagrams, which I'll just use a row. What you really need to remember is that these augmented diagrams with the on-diagonal points, they have an event corresponding to every simplex or every vertex, right? There's this one-to-one relationship between the vertices of the complex and points of the diagram, whereas we don't have that with the non-augmented diagrams. So that's the most important difference here. Okay. All right, so we're going to start talking about sets of diagrams. So we'll use this notation where if K is our simplicial complex embedded in some Euclidean space, and we have a set of directions S, capital S, then we'll just use this notation rho or rho hat with K and S to just denote the parameterized set of diagrams and that correspond to all those directions in the set S when filtering over K. Okay. So an example of this is maybe I take augmented diagrams. My simplicial complex is the one we looked at before, and I take my set to just be the whole sphere of directions, right? And what do I get? Well, I get this sort of movie of persistence diagrams, right, as our direction swings around. And that uncountable set, that uncountable collection of diagrams is denoted with this notation. Okay. All right, so our last really important sort of vocab word is the word faithful. So given a set of diagrams, we say that it's faithful if only one simplicial complex could have generated that same set. So a more sort of notationally heavy way of writing that is in this line. But really what I want to think about is if I hand you a set of these diagrams and you can tell me exactly without any ambiguity what simplicial complex generated them, and you can reconstruct it, then we say that that set is faithful. All right. So the first non-trivial example I can think of is we just have a single point in R2. Let's work on building a faithful set for that. So let's start with augmented diagrams. Okay. So if I come up with this E2, this upward vertical direction, what do I see in my diagram? I see that there's one connected component born at this height. And I see that there's exactly one vertex, no more, no less, right? Because we have this one-to-one relationship between vertices and points in the diagram. Okay, so I know there's one vertex. I know its y coordinate. I don't know its x coordinate yet. So this is an example of a not faithful set, right? Any point along this dotted line would give me the same persistence diagram. But if I come in with the second direction, so in the E1 direction, pointed horizontally, I still see there's exactly one vertex. And now I know its x coordinate, so I know its x and y coordinate. So that's an example of a faithful set. I can tell you exactly what simplicial complex, embedding everything about it, generated that set of two augmented diagrams. Okay. If I use non-augmented diagrams, the story changes a little bit because now I don't have this one-to-one relationship between vertices in the complex and points in the diagram, right? So now there's sort of this whole unexplored region that I can't be really sure what's going on in there. There's all sorts of stuff that could have happened. For instance, maybe I have an edge there, and the non-augmented diagrams would be identical. So I don't yet have a faithful set just using these two directions. So somehow I need to make sure that I know what's going on in this red or pink region. So if I come along with a third direction that kind of squashes out that unexplored region, now I can tell, okay, there really is just one vertex, nothing else going on, and I know its coordinates. So I have, again, an example of a faithful set, this time with size 3, cardinality 3. Okay. All right, so some background work. You may have heard these types of questions or thinking the phrase in terms of the persistent homology transform. That might be a familiar kind of term. And that was introduced in 2014 by Turner et al. And they showed that if you take the whole sphere of direction, so every possible direction, and you use those non-augmented diagrams, then you have a faithful set, at least for embedding dimension 2 and 3. At Montana State, we found a finite faithful set of augmented diagrams for graphs. We later improved these results, and then most generally, we were able to extend these results to simplicial complexes in arbitrary finite dimension. Okay, and around the same time as the first bullet point, Curry and others were bounding the size of a faithful set of non-augmented diagrams. That's also important to mention. Okay. All right, so I want to really just take a moment to emphasize the most general of those results that I mentioned from Montana State. So what is this saying? If I have a simplicial complex, I can find an explicit set of directions that makes a faithful set. I know exactly which directions I need given a particular simplicial complex. Okay, so that's important to keep in mind. We know the set of directions, or a set of directions. Okay. All So we have a set of directions. Can we make that set smaller? So that result I had just a second ago, that explicit set that we knew was faithful, it doesn't very, it's not minimal. There's kind of a lot of overkill in how we formed the set. So it's probably almost certainly not minimal. So, that leads us to the question, if I have a simplicial complex K, what is the cardinality of a minimum faithful set of either augmented or non-augmented? That's actually, if I may say so, I think a really hard question. So maybe a more approachable question is, what is the effect of using augmented diagrams versus not? How much do these on-diagonal points really help us? How much do they matter? And then lastly, can we find an example of a simplicial complex whose minimum faithful set has a large cardinality or larger than we expect? And that's what we're going to focus on for this section, finding simplicial complexes who have surprisingly large minimum faithful sets. Okay. Let's go ahead and start with augmented persistence diagrams. So if you start playing around with this, drawing simplicial complexes, trying to find their minimum faithful sets, you're going to quite likely see the number d plus 1 come up a lot, where d is the dimension that you're embedding your complex into. So it's independent of the size of the complex. One of my ongoing goals is to understand exactly when this happens and when it doesn't. But it's not too surprising of a thing to see, right? So remember, our augmented diagrams have an event for every simplex in the complex. So it shouldn't really matter how big the complex is, right? If the complex is bigger, you'll have more points in the diagram. So it kind of scales in a nice way. So it would be actually surprising if we could construct a complex whose minimum faithful set it depends on the size of the complex. And that's actually what we're going to do. So I think this is really cool. So get ready. All right. So our construction is as follows. So we have on the left, we have K, on the right, we have K prime. They have the same vertex sets, but just different edge sets. So we're assuming they're sort of embedded, overlaid, but I've drawn them separately, just different edge sets. So let's just, as a kind of orienting exercise, let's think about if I come through with this horizontal direction, sweeping from left to right, like my mouse is going, would my augmented persistence diagrams be able to tell the difference between K and K prime? Well, at the height of V1, right, I see a connected component born that lives forever. At V3, same thing for both K or K prime. I see a connected component born. At the height of V4, well, in each, V4 is an endpoint of an edge. So that's going to correspond to an instantaneous event, a point on the diagonal. So the same. And then in both K and K prime, V2 is also the endpoint of an edge. So I'm also just going to see this instantaneous event. So the augmented diagrams, at least in this left to right horizontal direction, are identical when I look at K versus K prime. So that direction, you can't tell the difference between K and K prime. So what directions can tell the difference? We can quantify that by what I'm calling this region of observability. So it's this gray shaded region. So anytime I take a direction from this gray shaded region, I'll be able to know for sure if I'm looking at K or I'm looking at K prime. Any direction in this white region, I can't tell. Okay. So if I'm going to have a faithful set of augmented diagrams, I for sure need to have a direction coming from this gray region. Otherwise, I don't know if I'm looking at K or K prime. And crucially, I have control over how big this region is, depending on how I embed my two edges. So as I move these edges closer to collinear, this region is going to shrink. So think about like taking V3 and pulling it up a little bit. That's going to shrink this gray region. Okay, so what does that allow us to do? That allows us to arrange, calling them clothespins, right? As many clothespins as you'd like, and in such a way that these gray regions actually don't overlap. So remember that in order to have a faithful set, we need a direction from each of these shaded regions. Well, that has to do with the size of the complex, right? And in particular, the number of vertices. So already we're seeing a number that's bigger than that mysterious D plus 1 that I was talking about, right? Here, D is 2. Okay, so say it a little more formally, the worst case cardinality of the minimum faithful set of augmented persistence diagrams is bounded below this big omega by the number of vertices, n0, number of vertices. Okay, on now to non-augmented diagrams. So we don't have this extra information of the diagonal points anymore. Can we make a simplicial complex who requires a lot to have a faithful set? Okay, so we had an example of a single point from before, right? And there was this phenomenon we observed where we had this unexplored region, and we kind of had to squash it out, right? We needed a third direction. More mathematically, we could say that the intersection of closed half spaces above the point with respect to all the directions needed to only contain the point and nothing else, right? So my third direction, if I look at the intersection of all these half spaces, it's just the single point, no extra space. Okay, so we can extend this or generalize this idea to higher dimensional simplices, and we're going to call it, I'll flash the picture here, we're going to call this the envelope of the simplex. So it's just the intersection of all these closed half spaces that are above of the simplex. So if my simplex is sigma and my direction set are these two directions, lowercase s and s prime, what would the envelope be? Well, as soon as I kind of run into the simplex, I look at the closed half space above it, and I take the intersection of those half spaces. So it's all this shaded region. And just like the point, where we wanted the envelope of the point to kind of be tight and only have the point and nothing else. The same is true for maximal simplices. So maximal meaning not a face of anything higher dimensional. So if we want to have a faithful set of non-augmented descriptors, we have to have sort of tight envelopes for all the maximal simplices. All right. So this condition of having tight envelopes, it's going to require a lot of directions that are perpendicular to a simplex. Of course, as long as you have high enough codimension. So why is that true? If we didn't have a direction perpendicular to a maximal simplex, there's all sorts of behavior that can occur sort of in this region below. For instance, like this red edge, we wouldn't be able to detect. But once we swing that direction around to being perpendicular, that kind of prevents any potential bad behavior or invisible behavior, right? And the same is true going the other direction. Okay. All right. So in general, if we have a K simplex living in RD, what do we need to make the envelopes tight? We need D minus K plus 1 perpendicular directions to maximal simplex. And of course, the envelopes also need to match the dimension of the simplex. Right? All right. So, okay, what are we doing? We're trying to build a simplicial complex whose minimal faithful set is as large as we can make it. So let's, vertices turn out to be a little too trivial. Let's focus on edges. That will kind of maximize this number of directions. D minus 1 plus 1 is just D, right? Okay. Unfortunately, all the pictures that are interesting are in higher dimensions than I can draw. So here's my highest dimensional picture. We need to keep in mind that if we have a collection of N1 edges living in RD, the number of directions that are, or the collection of directions that are perpendicular to that entire set of edges is parameterized by a sphere, a D minus the number of edges minus 1 sphere. So how can we see this in our picture? So suppose we just take this single green edge. So we have one edge. So we have 3 minus 1 minus 1. We should have a 1 sphere of directions perpendicular to it. And we do, right? That's that green circle, that green S1. Okay. Same thing for the blue edge, right? And how many directions, or what are the directions that are perpendicular to green and blue simultaneously? Well, we have a copy of S0, right? You can come from above, you can come from below. That's the intersection of these two S1s, okay? And in general, for higher D, larger collection of edges, we can say the same thing about the sphere that parameterizes the perpendicular direction. Okay, so our construction would be to put a handful of edges in RD in general position, and try to count what is the minimum number that I need to have tight envelopes and have the envelopes, I'm saying this, and have the envelopes be one-dimensional, right? So that they have a hope of containing the edges and nothing else. Okay. So here's my attempt to draw a picture in R7. There are 5 edges here, right? So, yeah, how many directions are perpendicular to all 5 edges at once? We had d minus the number of edges minus 1. So 7 minus 5 minus 1. We end up with a copy of S1. So the directions perpendicular to this entire collection of edges is parameterized by S1. We have uncountable many choices. So let's choose d minus 1 of them. So we'll have 6 directions that we're choosing that are perpendicular to all the edges in our collection. Why didn't I choose D? If I choose D, then the envelopes are going to be 5-dimensional. So I can't just do that. It's not quite as simple as that. Okay, I'm not quite done yet, right? I need a total of D directions perpendicular to each edge. So for each edge, I'm going to choose an additional direction that's perpendicular to only the edge. And that's a total of the number of edges more directions. So I have D minus 1 perpendicular to everything, and N1, the number of edges, additional direction. Okay. All right. So we're able to see that the worst case cardinality of a minimum faithful set, if we're looking at non-augmented diagrams, is the number of edges plus D. Sorry, bounded below. Yeah. All right. So let's pause for a moment and notice that in everything I've said up to this point, I have never used a single burst depth pairing. I've only used actually degree 0 information. And that's kind of because we're only looking at graphs, but really the information we're using is very simple. I could have, just gotten away with Euler characteristic, or just gotten away with Betty number, or just gotten away with degree 0 information. So the theorems that I had before, I can actually update them a little bit and make them more general because I didn't use the birth death pairing information. So these bounds that we found actually hold for Euler characteristic curves, Betty curves, their augmented versions, etc. And we'll talk more about these different types of descriptors here in a second. But I just wanted to mention that these are actually more general theorems than what we were focusing on. All right. So you might be wondering, will it ever matter what descriptor type we choose? Maybe it's not too hard to believe that it will eventually matter, or in some cases it will matter. Perhaps more interestingly, will it consistently matter, right? So like, will one descriptor type always be a better choice than the other? Or are there situations where it flips, right? Are there certain simplicial complexes where one descriptor type performs better than the other? And that's going to lead us into our next section. So ordering classes of descriptor types. All right. Okay, so remember, right, in what came before, we were talking about persistence diagrams. We chose to record homology pairings. We didn't really need to. We could have chosen to record Euler numbers. That a record of that throughout the filtration would have given us what's called an Euler characteristic curve, just a record of how the Euler number changes. We could have recorded the Betty number, and that would have given us, or Betty numbers, and that would have given us the Betty curve, just a summary of how that changes. And we could get even more creative. We could have recorded the precise coordinates of the lowest vertex, the number of edges in the first Euler connected component. Not sure why you would want to record this, but you certainly could. There's all sorts of, let your imagination go. You could record any number of topological invariants, right? So in general, I'm going to define a topological descriptor very broadly as just a map whose domain is a collection of finite filtered simplicial complexes. So persistence diagrams fall into that category, as do some of the more familiar things like Euler characteristic curves, etc. Okay. All right. Okay, so let's motivate ourselves with two sort of thought experiments. So remember in the last section of what I was talking about, we saw the example of a single point in R2. And when we were looking at augmented diagrams, our faithful set could be size 2. But when we looked at non-augmented diagrams, we had to have size 3. So somehow the non-augmented diagrams were sort of less efficient at making a faithful set. And it feels like, if we're going to be starting to order types of descriptors, it feels like non-augmented diagrams, at least from what we've seen, maybe should be weaker than augmented diagrams in some way. Okay, thought exercise number 2. Suppose I invent a type of topological descriptor that I'm going to call negative rho. And it's very similar to persistence diagrams, except that if the input is a lower star filtration in direction S, it's going to give me back the persistence diagram corresponding to direction negative s. So it's kind of just like flipping stuff on its head. And it feels, at least to me, like this negative rho that I made up should be equivalent to regular rho in some way. There's not any more or less information really going on. It's just presented differently. Okay. So these two sort of thought experiments are going to lead us to define strength equivalence classes. So given two different topological descriptors, A and B, we'll say they have equal strength if for all simplicial complexes we have either of two things. So first, the minimum faithful set of type A has the same cardinality of the minimum faithful set of type B. So A and B sort of are equally efficient at making a faithful set. Or, it might be the case that because of the type of descriptor, because of the type of complex, there just is no faithful set, but it has to be true for both A and B. So kind of in either situation, A and B are performing equally well at making faithful sets in terms of cardinality. And we'll use this notation for equivalence class, bracket A equals bracket B. All right. Okay, so our goal is to order strength equivalence classes. I'm sorry, this is kind of a lot to read. But suppose we have two equivalence classes and we want to think about ordering them. We say that A is weaker than or equal to B using this notation. If so if I give you a simplicial complex and I ask you about faithful sets, you can always find a faithful set that's equal to or smaller than the faithful set of type A. I don't know if that was a complete sentence. Sorry. So there always exist faithful sets of type B with cardinality less than or equal to cardinality sets of faithful sets of type A. So A is somehow kind of less efficient than B. So it's kind of this weird reversing of direction that's going on, right? It takes fewer of type B, we see that B is stronger. Okay. All right, so this is my disclaimer slide that these are well-defined relations, the equivalence class as well as the ordering. All right. Okay, so to get a grip on these definitions, they were defined for general topological descriptors, but let's focus on some hopefully more familiar examples. Right, so we have Euler characteristic curves, both the augmented and non-augmented versions. What does this hat mean? Similar to the augmented persistence diagram, where it's sort of like if you had index filtration, what would the corresponding Euler characteristic curve be? The augmented and non-augmented Betti curve, so beta and beta hat, and then our old friend augmented and non-augmented persistence diagrams. So hopefully the notation here is not too hard to remember, right? Euler characteristic is a pi, beta curve is a beta, Betti curve is a beta, and persistence diagrams are again the rho. All right, so we have 6 descriptors we're going to try to order. So immediately we get a few results just from a reduction type argument, right? So we see that if I have a non-augmented descriptor and I compare it to its augmented version, we have this less than or equal to relationship. And this is just kind of immediate, right? If I have a faithful set of non-augmented descriptors and I add on these extra augmented points, I'm not losing any information, right? I'm not becoming less efficient in a sense. So through this reduction argument, we can show that we have these relationships between non-augmented and augmented counterparts. All right. Again, through reduction, we can show that we can relate this set of 3 non-augmented and this set of 3 augmented. Again, just through a reduction argument. So notice if I give you a persistence diagram, you can tell me the Betti numbers throughout the filtration. You can tell me the Betti curve. And if I tell you the Betti numbers, you can take their alternating sum and give me the Euler characteristic curve, right? Okay. And same for the augmented side of the world. Okay. So those 2 results were just a reduction argument. I think maybe a more nuanced result is the following. We're able to show that augmented Betti curves are strictly less than augmented persistence diagrams. Okay. So let's kind of talk through why this is true. So we already know through the reduction argument that we have this less than or equal to going on. So what we need to show is that they're not equivalent as strength classes, right? What does that boil down to? It means that there exists some simplicial complex that requires strictly fewer augmented diagrams, then augmented Betty curves to form a faithful set. So we need to identify such a complex. All right. So here's that complex, K. So I'm claiming that it requires strictly fewer augmented diagrams than augmented Betty curves. So let's look at why that is true. The first thing I'll say is that if I just take E1, E2, the vertical and horizontal directions, I have a faithful set of augmented diagrams. Now there's a lot baked into this bullet point, so let's kind of walk through why this is the case. So let's first focus on this horizontal direction. What do I get from the diagram corresponding to the horizontal direction? Well, at this first slice, I see, okay, there are 2 vertices here. I know their x-coordinate, and 2 vertices here. I know their x-coordinate. So I know there are exactly 4 vertices. I know that there are 2 x-coordinates that are shared. And similarly, in the vertical direction, I see there are 2 vertices. I know their y-coordinate. 2 more vertices. I know their y-coordinate. So already I know that there are 4 vertices, and I know their coordinates. I know their precise location. Okay, what about edges? How do I know what the edge set is? Well, from this horizontal direction, I'm going to see at the height of V4 and V2, I see that because there are 2 instantaneous births and deaths, I know that there are 2 edges that are completed at that height. Okay. There's all sorts of, edge sets that would have that property. So I need this vertical direction to then tell me that because I have a death at V4, I know that I have this sort of shape. Okay. So the information of those 2 diagrams combined allows me to completely reconstruct without any ambiguity K. I know exactly what the underlying simplicial complex is. All right. So let's look at now at augmented Betty curves. So I claim if we're going to have a faithful set of size 2, which we won't, but assume to the contrary that we do, we're going to need directions corresponding to 2 of the 4 cardinal directions. And that's just a feature of, if we want to know the vertex locations, it has to relate to the grid that we've specifically put K on. Otherwise, we won't know the vertex locations. Okay, so we have to have the 4 cardinal directions. But in each of the cardinal directions, if we're looking at just that augmented Betty, so it doesn't have this birth-death pairing in particular, so we don't get this death that's paired up with a birth downstairs, the augmented Betty curves can't distinguish K from K prime. So we have this sort of contradiction. We can never have a faithful set of size 2. Okay, so it has to be at least size 3. Is there one of size 3? Maybe, I don't know. The important thing is it has to be 3 or larger. And what we've seen is, right, there was a faithful set of augmented diagrams with size 2. 2 is less than or equal to 3, right? So we found an example that shows that these are in different strength equivalence classes. Okay. All right, so to kind of summarize what we went through, right, our vertical arrows were that first reduction argument, right? Just forget the data of the augmented descriptors. So like forget the on-diagonal points, you end up downstairs. And then our rows were again through a reduction argument, right? Give me a persistence diagram, I can tell you the Betty numbers. Give me the Betty numbers, I can tell you the Euler characteristic. And then this last strict inequality is what we just finished talking about, right? Showing that the augmented Betty curves are not in the same strength equivalence class as augmented diagram. Okay. All right, so in ongoing work, I really feel that perhaps we actually have a total order on our set of 6. So we have our non-augmented descriptors and then our augmented. So what would the new thing be here? It would be this strict inequality in the middle here, relating non-augmented persistence diagrams to augmented Euler characteristic curves. That feels true in large part because of what we discussed about the envelopes needing to be tight in all these perpendicular directions. And the size of the minimum faithful set really blows up for these non-augmented descriptors, where that just isn't really the case on the augmented side. So what would we need to show in order to prove this conjecture? Well, we already know that they're in different strength equivalence classes. I didn't really tell you why, but a single edge in R2, if you compare the the minimum faithful sets, you can find that they can be true. So we need to show that they are comparable. And how would we do that? We need to show that there is no simplicial complex that will ever require fewer non-augmented diagrams to form a faithful set than augmented or their characteristic curves. And somehow it's proven to be more difficult than finding just a single example like we did in our augmented Betty curves, augmented diagrams, right? We need to show that this is true for all simplicial complexes. Okay. Another ongoing goal is to just better understand how these non-augmented descriptors relate, right? We got, oops, this should be a strict inequality, excuse me, but we got the strict inequality between the Betty and the diagrams. Is it possible to get that in the non-augmented side? And again, because things are just so unwieldy on the left side here, because we have all these perpendicular directions and these tight envelopes requirements and all sorts of things going on, it's proven to be a little bit more difficult. And then the big overarching goal, whether it's attainable or not, is if I have a simplicial complex and I know its size, I know its number of vertices, number of k-simplices, etc., can I tell you the cardinality of a minimum faithful set in terms of the size of the complex? All right. Okay, so with that, I have a few references and happy to take questions.
Great, thank you. Let's all thank Anna together by clapping together. So please unmute yourself, everyone. Okay, so now we can all ask questions. Maybe I'll start with one while others think if they have questions. Namely, in that slide actually that you have right here, you have these vertical arrows and you wrote strictly smaller on all of them. But I think you didn't show us why it's strictly smaller. You just argued why it's smaller or equal. And especially for the beta curves, it kind of surprises me a bit that it's strictly smaller because it doesn't seem to me like there's so much more information in the augmented beta than in the non-augmented one. Maybe you can elaborate a bit on that or something.
Yeah, so good catch. I didn't tell you why these are strict inequalities. So we know they're less than or equal to because of reduction, right? So what do we need to show in order to show that this inequality is strict? We need to find an example of a simplicial complex that requires strictly more non-augmented than augmented. And the example is, or an example is just a single edge in R2. So let's think about, let's start with the augmented case, right? What would a minimum faithful set look like? So maybe you can see my charades here. So I have an edge that's maybe oriented vertically, and maybe I come up vertically. What do I see? Well, I see, that there are two vertices. I know their heights, and I know that they're connected by an edge. Okay, and then I come in with a sideways direction. I see their x-coordinates. So 2 does the job for augmented, and that's true for any of the 3 up top. Downstairs, however, maybe let me see if I can. I had this thought that I would draw. I don't know if that's going to be easy or not. Maybe not as easy as I thought. Okay, so for the non-augmented, suppose I come up and sideways, right? Am I finished? Well, no, because kind of maybe to the right here, I could have like a 2 simplex hanging off, or I could have an edge hanging off. So that's that condition on the number of perpendicular directions. I need a direction perpendicular this way, and I need a direction perpendicular this way to have that envelope condition satisfied. So I've seen that, okay, so for the top row, I can get away with just 2 directions. For the bottom row, I need 3 or more.
Okay, thank you.
And that's true for any of the columns, yeah.
Nice. Okay, then I'll also leave some time for other people to ask questions. Does anyone have a question?
I wanted to ask a question. So just to clarify, so let's say we have a fixed topological descriptor, and you described this minimal cardinality, right, that would be needed. So that cardinality, that set of directions would be that set of directions, it needs to distinguish how the simplicial complex is embedded and also distinguish that simplicial complex from any other simplicial complex. Is that right?
That's right. So I need to know without any ambiguity exactly what simplicial complex I'm looking at and where it's embedded. Yeah, exactly.
I see. I see. Right. Okay. So I see. Right. So you ask for a particular simplicial complex, right? What's the cardinality needed to determine its embedding exactly and distinguish it from any other complex?
Yeah.
Do people ask this question for vertex location? So let's say I fix a number of vertices. Could I ask how many directions are needed to determine the simplicial complex on top of these fixed vertices with fixed?
Oh, so if you already know the vertex locations, that's part of the kind of the input.
Yeah.
Right? Yeah, definitely. So I mentioned way back at the beginning some results about finding an explicit set of almost certainly not minimal, but an example of a faithful set. And in that, the way that we approached it was to first find all the vertex locations, and then on top of that, find all the edges, and then on top of that, find all the two simplicities, and kind of build up an order of dimension. And so just kind of like a brief, I think it's kind of an interesting technique for edges. What we did was we used something that we called in degree, which means kind of what you might think from the word, right? So if you have a direction and you look at a vertex, how many edges are coming into the vertex with respect to that direction? So kind of below the vertex and adjacent to the vertex. And you can read that off of the diagram, actually, the augmented diagram. And so what we did is, if we have a pair of vertices that we know, what their coordinates are, but we don't know if there's an edge between them or not, then what we can do is we can choose a direction first that's, perpendicular to the pair of edges and look at the in degree, and then just tilt the direction ever so slightly so that it misses the potential edge, and see if the in degree changes at all. If it does change, we know we dropped off an edge by that tilt. But if it doesn't change, we know that we didn't miss it. There's no edge there. So that was, I guess, kind of at the heart of the method that was used there. That's not to say there are more efficient methods or different techniques, but that's an example of one. Yeah.
Great. Yeah. Thanks so much.
Does anyone else have a question? I would have another one, but I want to let other people also be able to ask questions. Okay, I'll just ask. People can ask after me. So you said that in this very beginning example, actually the one that you have at the top of the slide here, that even the augmented persistence needs a direction in this thin slice in order to distinguish them. So all the other directions would not distinguish this two edges.
Mm-hmm.
I was wondering the merge tree would distinguish them, right? So is there some work in the direction, or do you by chance know anything in the direction of reducing the number of directions even more by having something in some sense richer like the merge tree, but then the merge tree is only measuring zero homological information, so also weaker, but maybe for certain situation it might be stronger. I don't know. Any thoughts about the topic maybe?
Yeah, that's really interesting. Yeah, I have to say I'm not as familiar with the merge tree side of things. But perhaps, right, and there are examples of topological descriptors that they aren't comparable, where they perform better in some simplicial complexes, and the other one performs better in other settings. Yeah,
that's
so
also what my gut feeling would say.
Sorry?
It's also what my gut feeling. My gut feeling would also say that it's probably neither stronger nor weaker than persistent homology. In some situations stronger, in some situations weaker, or something like that. But yeah, it would be interesting too.
Yeah, I'll have to think a little bit more about that. I like that because it's sort of a more real world example of potentially non-comparable descriptors. The examples I have are kind of cooked up, so that would be nice to have a more realistic example. Now think about that.
Cool. Okay, last chance for asking questions.
Yeah, just to piggyback off of what Teresa was saying, which topological descriptors are not comparable?
Sure. So as I mentioned, the examples I have in mind are fairly designed, and they're not really realistic for what people are using in applications. So if we take a topological descriptor to be any map out of finite filtered simplicial complexes, suppose, for instance, that we take our topological descriptor to report back, for any filtration, it reports back the number of vertices and the coordinate of the lowest vertex. That's a fine description of a filtration, right? So let's compare that descriptor with augmented persistence diagrams, right? So suppose we take our example of a single point. We saw a minimal faithful set of augmented persistence diagrams needed 2 directions, right, to get both x and y coordinates. But in the descriptor that I just invented, really just exactly for this purpose, it would only take 1 direction, right? From 1 direction, we know there's only 1 vertex, we know the coordinates, okay? But for any more complicated simplicial complex, like an edge, my invented descriptor won't be able to form a faithful set at all, right? It can only tell me the number of vertices and the coordinate of the lowest. Nothing about the higher dimensional things or whatever. Whereas an augmented diagram can form a faithful set. So in that, really engineered example, we have 2 simplicial complexes, one where my invented descriptor works better, and one where my invented descriptor won't work for, it won't work
Okay,
at all.
I see.
Yeah.
Very cool.
Great. Then before I'll end the recording, I want to thank you again for this particularly great talk.
Thank you.